Hi, welcome to Mathematics of Chemistry Review Part 3. My name is Dr. English. Today we're going to be talking about a review of empirical and molecular formulas. Specifically, we're going to be looking at, a quick review of empirical and molecular formulas, calculating empirical formulas, examples of how to calculate an empirical formula, calculating molecular formulas, and finally, some examples of how to calculate a molecular formula. So let's start off with a little review of empirical and molecular formulas and basically just going over the definition of what these two things are. So a molecular formula. A molecular formula is going to give you the kind and number of each element in the molecule. Now remember, when you see the word molecule gives you a lot of information about what you're dealing with. If it is a molecule, that means, in general, we're going to have covalent bonds, which means that if we have covalent bonds, we're going to be dealing with nonmetals. Nonmetals are going to be part of this compound. So when you see the word molecule means covalent bonding is involved, and we're dealing with nonmetals, which is why I have here only nonmetals. So an example of a molecular formula might be something like this: SO2, sulfur dioxide, both which are nonmetals, or P4O10, tetraphosphorus dicoxide, both nonmetals. An empirical formula is different than a molecular formula. An empirical formula is a formula that gives the simplest whole number ratio of the atoms of the element. So for example, here we have caffeine. The molecular formula of caffeine is C8H10N4O2. To figure out the empirical formula for this, we have to look at all the numbers and figure out what number will divide into all of these numbers equally. So if we look at this, we see that 2 is the highest number that will divide into all of these numbers equally. So we're going to say 8 divided by 2, 10 divided by 2, 4 divided by 2, and 2 divided by 2. So my empirical formula will be C4H5N2O. And then again, we don't need to put the 1. There is an assumed 1 right here at the end of the formula, but it does not need to be involved and typically is not seen. Now let's look at an example of calculating an empirical formula. A compound is 92.2 grams of carbon and 7.76 grams of hydrogen. Calculate the empirical formula. The first thing that we want to do is look for the two given numbers. And could there be more than 2? Of course there could, but in this case we have just 2 given numbers. So the first one is 92.2 grams of carbon, and the second one is 7.76 grams of hydrogen. The next step here is that I want to convert each of these gram amounts into moles. So I'm going to put a multiplication sign and a line, a multiplication sign and a line. And what I tell my students is that whatever unit you start with goes on the bottom. So I have grams of carbon to start with, so grams of carbon will be on the bottom. Here we'll have grams of hydrogen. We want to convert to moles, so 1 mole of carbon will go on the top, 1 mole of hydrogen will be on the bottom. I know that the atomic mass of carbon is 12, and that will equal 1 mole of carbon, and I know that 1 gram of hydrogen will equal 1 mole of hydrogen. So now what I want to do is convert each of these into moles. So grams of carbon cancels grams of carbon. 92.2 times 1 divided by 12 will give me 7.68 moles of carbon. And when I convert grams of hydrogen, and that cancels grams of hydrogen, when I convert that into moles, it'll give me 7.76 moles of hydrogen. The next thing that I want to do is divide by the smallest number of moles. So out of these two, 7.68 moles is the smaller number. So I'm going to divide this by itself, 7.68, divide 7.76 by 7.68, and any number divided by itself, of course, will be 1. And 7.76 divided by 7.68 gives us roughly 1.01. Now the reason why I'm doing this is that ultimately these are going to give me my ratios or my subscripts in my empirical formula. So based off of this, I can see that these numbers basically round to 1. So the empirical formula for 92.2 grams of carbon and 7.76 grams of hydrogen will basically be C1H1. Now it's not typical to see 1s in formulas. So the more common way of seeing this would just be CH with the 1s assumed to be part of the formula. Let's look at another example of calculating an empirical formula. A compound was analyzed and found to contain 13.5 grams of calcium, 10.8 grams of oxygen, and 0.675 grams of hydrogen. What is the empirical formula? So I challenge you to pause the video and see if you can do it on your own, or if you feel like you need a little bit more help and would like to see another example, feel free to watch along. So let's start out with our numbers. We have 3 numbers given here. The first one is 13.5 grams of calcium. The second one is 10.8 grams of oxygen, and the last one is 0.675 grams of hydrogen. And like we did with the previous example, the first thing that we want to do is write setups to convert all of these masses into moles. So I'm going to say multiplication sign and a line, and the atomic mass for calcium is 40. So 40 grams of Ca is equal to 1 mole of Ca. For oxygen, we have 16 grams of oxygen is equal to 1 mole of oxygen. And finally, for hydrogen, we have 1 mole of hydrogen is equal to 1 gram of hydrogen. And I'm going to put my equal sign in for all of these. And this first step is just doing a mass to mole conversion. Now let's go through and solve these. So we know we have these set up if the unit that we start with can be canceled by the unit on the bottom of our first ratio. So grams of calcium cancels grams of calcium. 13.5 times 1 divided by 40 is 0.3375 moles of calcium. Let's look at the next one. 10.8 grams of oxygen times 1 divided by 16, and the answer here is 0.675 moles of oxygen. And for the last one, 0.675 grams of hydrogen times 1 mole divided by 1 gram will give us 0.675 moles of hydrogen. And again, the next thing that we want to do is figure out which one is the smallest number of the 3 and take that number and divide it by the rest. So if we look here, we see that the moles of calcium is our smallest number. So I'm going to divide this by itself, so 0.3375, divide the moles of oxygen by 0.3375, and finally my moles of hydrogen by 0.3375. So any number divided by itself is going to be 1. 0.675 divided by 0.3375 is going to be approximately 2, and the same thing down here. And remember, these are all the mole ratio of the elements that's involved in this compound. So legitimately, we could write Ca1O2H2, but to me that looks a little strange. I'm not used to seeing a formula written like that. So for me, the more correct way of doing it would be Ca parentheses OH and parentheses 2. Because I look at this and I think, oh, I know that formula because the Ca can be plus 2 if I uncrisscross it. Here we have a hydroxide polyatomic ion, that's going to be minus 1. And if I uncrisscross it, it all makes sense to me. But in the grand scheme of things, what are we looking for? What's the skill that we want you to be able to perform? Can you calculate an empirical formula based on information provided to you? Which means This is all that we're really looking for, the elements with possible subscripts to show the ratio of elements within this compound. Now let's talk about calculating molecular formulas. Given the molecular mass of a compound and an empirical formula, find the molecular formula. Here's the steps that you're going to follow. Calculate the gram formula mass, or molar mass, of a given empirical formula. So with the formula that you're given, you find the gram formula mass of that. Divide the given molecular mass by the calculated empirical mass that you just found. The resulting calculation will be a whole number. This number will be multiplied by the subscripts in the original empirical formula. Let's see an example of what this would look like. A compound is an empirical formula of CH2 and a molecular mass of 56 grams. What is its molecular formula? The first thing that I'm going to do is write out my empirical formula, which is CH2. And then I'm going to find the gram formula mass of my empirical formula. So carbon is 12, each hydrogen is 1, so the gram formula mass of CH2 is 14 grams. And then the 56 grams is a given, and that is my total molecular mass. Now I want a whole number here, so what I'm going to do is basically take the molecular mass, so I'm going to abbreviate this, take the molecular mass and divide it by the calculated empirical mass that we just did with the 14. So my larger number is going to be on top. So 56 divided by 14 gives me 4. So now what you want to do is you want to look back at your original empirical formula, which is CH2. Now we know the ratio to carbon to hydrogen here is 1 to 2. So for simplicity's sake, I'm throwing in the 1. We want to take that 4 now that we calculated and multiply all the subscripts in the empirical formula by that number. So my new molecular formula is going to be C4H8. And the way that I can double check myself is to say, well, if I reduce this back down, will I get my original empirical formula? And in this case, we will. So the correct empirical formula here that we found is C4H8. Let's look at another example of calculating a molecular formula. And again, you can either pause the video, try it on your own and check your work, or just follow along just to get another example. Find the molecular formula of ethylene glycol, which is used as antifreeze. The molecular mass is 62 grams per mole, and the empirical formula is CH3O. So the first thing that I'm going to do is write out my empirical formula, CH3O, and find the gram formula mass of that. So I know that there is 1 carbon here, and it has an atomic mass of 12. I have 3 hydrogens here, each with a mass of 1, so that is 3. And then with my oxygen, I have 1 oxygen times 16 gives me 16. And if I add this all up, I find that the gram formula mass here is going to be 31 grams. Now what I want to do is take the molar mass, which is 62 grams, the larger number, and divide it by the smaller number that we just figured out for the empirical formula mass. So 31 grams. And when I do this, I find that the number is 2. So what I want to do now is rewrite my empirical formula, CH3O, recognizing that there's 1 carbon here and 1 oxygen here, and multiply all of those subscripts by 2. So my molecular formula here is going to be C2H6O2. And of course the check, like usual, is can I reduce the C2H6O2 back down to my original empirical formula? And I can do that. So I know I must have the correct molecular formula. So what did you learn in this tutorial? We did a quick review of the definitions of an empirical and a molecular formula. We talked about how to calculate an empirical formula, and then we did another example with it. We talked about how to calculate molecular formulas, and then finally finished up with one more example of how to calculate a molecular formula. Need more help? Feel free to contact me. Have a great day.